Oh, kind of tough. All right. That being said, let me share my screen. You should all be seeing the homepage here. Just somebody just tell me yes.
Yes.
All right. First thing is I will post tonight's video as soon as it's rendered. It'll probably be up tonight, if not tomorrow morning first. I'll probably do it tonight. But like I said, I think you guys all get an email to the link. It's kind of important. I think everything is important, is this worksheet solutions. What I've done here at the top here, last week I did a modified 3 PowerPoints, 4, 3, 5, 2, and I put all these together. Modified meaning they're not the exact ones that I had posted in the assignments and homework, but I modified them for the meeting. I kind of streamed them down and I added maybe a slide or two. I've done the same thing for tonight. I'm going to go through 6, 6, 7, 1, and 7, 2, but these are modified ones. So as we're going through them tonight, if you want to see, I have these modified PowerPoints on your computer. You can download them. All right, so the test is going to cover 4, 3, 5, 2, 6, 2, 6, 3, 6, 5, 6, 6, 7, 1, and 7, 2. So these are the answers, but more than answers, they're also screenshots. What I think would be helpful, just an idea, if I were taking this test, because using the calculator, we're kind of all over the place. In 4.3, we're using the math function. We're using permutations, combinations, and combinations. In section 5.2, you're going to second function vars, and you're coming down to normal cumulative, normal CDF. I'm sorry, in 5.2, you're coming down to binomial PDF and binomial CDF. But the idea is to get to the calculator functions in section 5.2 and even in 6.2, 6.3, and 6.5. You get to it by going second function, hitting the vars menu. All right, for 6.2, 6.3, 6.5, 6.6, you're going to normal cumulative. And for 5.2, you're coming all the way down to letter A and letter B, binomial PDF and CDF. So it may be a good idea just to, put a little note by your solutions. Hey, how am I getting to this menu? And that's kind of important because now when you get to section 7.1 and 7.2, you don't go to second function vars, you just hit the stat menu, you arrow to the right to test. And for 7.1, you come down to number 7 Z interval, and for section 7.2, you come down to number 8 T interval. So I'm saying it may not be a bad idea to put a little note. Hey, how do I get to this menu that I need to do this particular section? You get your positive and negative Z scores. Yeah, and you don't really need that because the calculator is going to give you an answer that's really, really close, but I gave it to you anyways. This is super important here. For section 7.1, you're going to need those critical Z scores for the levels of confidence. And then for section 7.2, you can't do it without having this T distribution. Not so much to get the confidence interval, but at first, just to get the error. The error is a T score times S over the square root of n, but I'll get to that. So this stuff is all here, so take advantage of it. Next thing I want to show you is obviously tomorrow the quiz opens up. And greetings all. It opens up tomorrow morning at 11 o'clock, and you've got until 11 o'clock on Thursday. But once again, once you begin the exam, you must do it in one sitting. What I have changed, you may or may have not seen this, I've actually given you an extra 15 minutes. All right, so 3 hours, my gosh. So time should not be a major factor. If I'm not mistaken, there's 40 questions, and majority of these answers are spot on. Unless you're doing something really wacky, you're getting an answer that's totally wrong. If you're not getting the answer, go back and do it again. You put something in wrong in your calculator because these answers are going to be spot on for the most part. And if they are off, they're only going to be off by a few 10,000s. All right, so 3 hours, which pretty much in 40 examples gives you, let's see, 40 examples, 3 minutes would give you 124. you probably got like 4.5 minutes per problem. All right, so some of these examples, maybe take 30 seconds to do. So that means you've got like maybe 8 minutes. So it's not a rush. I mean, your clock is clicking down. You don't want to spend a half an hour on a problem, but there's no need to rush because you can't go back, and that's for security purposes. All right, so that's the story. You've got all your stuff you need, and yeah, what I'll do is I'll be probably posting grades, submitting grades after 11 o'clock Thursday. So if you don't see your grade, because sometimes, well, if you need to know what your grade is, you can just shoot me an email. I'm not sure how fast the college puts it online. So if you need to know your grade, let me know and I'll give it to you. I'll email it to you. All right, let me stop this and let me open up what I need to open up, and that's section 6.6. And I want to share my screen. Make sure I'm still recording. I guess I am, so that's great. I want to do my slideshow starting from the beginning. All right, just as a review. All right, we're in section 6.6, which is part of chapter 6. Back in section 6.2, when we first began this, standard normal. What's it mean to be a standard normal? Well, your mean is 0, your standard deviation is 1. But all through chapter 6, and including in section 6.6, we're going to be finding the area to the left, the area to the right, and sometimes the area in the middle. All right, because area relates to probability. And the normal cumulative, second function vars, all right, normal cumulative, all right. You need a lower limit and an upper limit. Mean is 0 and standard deviation is 1. Here again, the lower limit is way out here at negative infinity, and then your upper is 1.13. You get the idea. Then he flips the script. This is where he gives you a lower and the upper, and you need to find the area, which is the probability. And then he flips the script. He gives you the area. He's looking for the X score. Well, it's a left-handed table. So the area the area, I'm going to say it again, the area that's associated with this value is the area to the left. All right, so he tells me the area is to the left. The shaded region is this. I popped into my calculator. Mean is 0 and deviation is 1. But sometimes he tries to play you. He gives you this area, but guess what? The area that's associated with this question mark is not this area. It's the area to the left. So I need to do some subtraction, find the area to the left, plop that in, mean is 0, standard deviation is 1. That's section 6.2. All right, section 6.3, non-standard normal. Same idea. We're finding probabilities which relate to areas. We have a low limit, we have an upper limit. The mean in this case is not 0. In this case, it's 60. The standard deviation is 4. Put that in the calculator, gives you the correct probability. And then we also have the inverse norm. We call that it's a left-handed table. The area that's associated with a value is the area to the left. In this case here, the bottom 81%, the area to the left would be 0.81. Mean is 70, standard deviation 11.5. There is there's an inverse norm here. All right, so section 6.2, find the area, then find the X value. And the same thing happens here, difference being standard deviation not 0 and mean not 1. Take that back. Mean not 0 and standard deviation not 1. And then we get to section 6.5. All right, the difference in 6.5 is you're not working with, in this case here, 1 year or one person or one whatever. You're working with multiple items. You're finding the probability of the mean of these multiple items falling within a certain range. You'll see, well, first of all, doing the test, it'll be labeled 6.5. All right, central limit theorem. So when you see those words, central limit theorem, and then what I've done for you in the exam, I've actually bolded out and I've underlined the fact that you're working with, in this case here, multiple years. What changes is you still got a low bound, you still got an upper bound, you got a mean that's not 0. The major difference is the standard deviation is the original standard deviation, in this case here, 14 inches divided by n. All right, N is the number, in this case here, number of years of snowfall. All right, central limit theorem. There is no inverse norm. All there is in 6.5 is give me the probability. All right, here again, I'll underline and bold out, but it'll be labeled section 6.5. It'll be labeled central limit theorem. You're saying to yourself, okay, central limit theorem. The standard deviation is calculated by taking the original one, dividing it by the square root of n, which will be bolded out. All right, brings us to section 6.6, the most challenging section in chapter 6. We're still going to be finding areas to the left and areas to the right and areas in the middle. There is no inverse norm in 6.6. There's enough to do just what we're going to do. Here's the deal here. It says normal as an approximation to binomial. Well, normal is this normal curve that we've been drawing, this bell curve. Binomial distribution is something we did back in section 5.2. So you're saying to yourself, well, why am I going to use a normal distribution to approximate something that I already know how to do? In the real world, you wouldn't do that. All right. This is just a section that the author throws in to have you play around with this normal curve. In reality, is you're not going to approximate something that you actually know how to find the answer to. Here's an example of something we did back in chapter 5.2, section 5.2. All right, certain college, 30% of the physics majors were ethnic minorities. If 10 students are selected, what's the probability that no more than 6? Key thing is, back in the binomial distribution, back in 5.2, we were working with discrete whole numbers like 10 and 6. All right, we went, to second function bars, and we came down to binomial, in this case, CDF, and we found the answer. So when we have a binomial distribution, we typically use only whole numbers for random variables. With the normal approximation, the normal curve works with items that could be decimals, like people's weights or people's heights, or maybe even people's ages. No one's exactly, 28 years old. Let's say we're talking to them on their birthday. They're 28.1 years old and so forth. Things that, end in decimals. So we're trying to approximate something that, is only whole numbers. We're trying to approximate it using something that uses this bell curve, something that's made for numbers that have decimals or could have decimals in it. So what changes? We're still going to be working with left and right, okay? He talks about number of successes being R, but our calculator doesn't use R, it uses X. X and R are one and the same. We're talking about probabilities, right? Our p-values. We haven't talked about Q in a long time. In fact, we haven't even had to use. We even haven't had to use it. We are going to use it in section 6.6. You remember that P plus Q equals 1. P and Q are complements. If I know P to find Q, I take 1, subtract P. This next part here, that n times P is going to be greater than 5 and n times Q. Don't worry about this. This will be in play. This is not an issue. But what's important now is, hey, he used to tell me what the mean was. He doesn't tell me anymore. I got to calculate, or my calculator has to calculate the mean. And how do we do it? We take n, which will be given to us, we multiply it times the probability of a success, P. What's even crazier is the standard deviation. Back in 6.5, it was the original one divided by the square root of n. That was, a little different than it was back in 6.2, where the standard deviation was 1. And then in section 6.3, it was something other than 1. Now we actually have to put the square root symbol and pop in an n value, pop in a p value, calculate what Q is, and then pop that in. So section 6.6 is all that in a bag of chips. It's a lot to it. There's a lot to it. All right, the key concept in this section, we present a method for using a normal distribution, a bell curve, as an approximation to a binomial distribution. Probabilities from a binomial distribution can be approximated using a normal distribution with a mean and standard deviation. But here again, in the real world, we wouldn't be doing that because we already know how to find the actual answer. Because a binomial distribution uses only whole numbers and our normal distribution is continuous, meaning it could have decimals, we have to use something called continuity correction. You'll know you're in section 6.6 because it comes after 6.5, and it'll be labeled, the problems at the very beginning will be labeled continuity correction. Oh, I'm in section 6.6. Here's the big deal. We've got to take these whole numbers that we're given. We're going to subtract 5/10 on one end, and we're going to add 5/10 on the other end. This is the continuity correction. What we're introducing here is some decimals. All right. And this is right off of Big Al, the video for section 6.6. Why we have to do that, all right, is that here's my histogram. If I overlay a bell curve, you can see what's happening here. My bell curve is talking about this area, which is not part of my bar. And then it gives me this area. It doesn't add this, it adds this area by mistake, and it cuts off this area by mistake. So to accommodate that, if this in the middle, this is my 8, notice, well, I would be putting my 8 right here. What continuity correction is telling me is take the 8, subtract 5/10 to 7.5 and add 5/10, you get 8.5. And then I'm going to have to figure out which way am I going? Am I starting at 7.5 and am I going to my right? Am I starting at 7.5 and going to my left? Maybe I'm starting at 8.5 going to my left, or am I starting at 8.5 and going to my right? In section 6.6, let me say this very succinctly. In section 6.6, if you're using a whole number like 8 or 7 for your lower bound or your upper bound, you are doing it wrong. One of your, either your lower or your upper is going to be a decimal that has it's going to be a 5/10 attached to it. It's going to be 3.5 or 7.5. There's going to be a decimal. If you're using a whole number for your upper or your lower, you're doing it wrong. It's going to be something with a decimal, and that decimal is going to be 5/10. All right, here again, this all gets down to 6.6, being able to take an expression in words and translating it to an inequality. All right, this actually goes back to section 5.2, binomial. Being able to take something in words and translating it to. So I put this down in. You may want to print this out, have this by your side if you have difficulty translating expressions to mathematical or inequalities. And this talks about the same thing. You know, first thing we're going to do, we're going to draw our bell curve. We're going to put our target value in, and then we're going to subtract 5/10 from that value and then add 5/10 from that value. Now, this is kind of important, you know, at least 8. Well, at least 8 translates to X is greater than or equal to 8. At least 8 contains 8. All right. So what I'm doing here is I'm starting to the left of 8, 7.5, and I'm going all the way out to positive infinity. Now, here's what happens with these. People get confused. They go, why am I starting at 7.5 when he says at least 8? And 7.5 isn't at least 8. Here's what I'm saying. Trust your inequality. At least 8 translates to 8 is X is greater than or equal to. And when that happens, it's going to appear like your shaded region isn't applicable, but it is because of continuity correction. Now, when you just have something like X is more than 8, which translates to X is greater than 8, well, I'm starting off at 8.5. I didn't want to start off at 7.5 and go to my right because I would include 8. More than 8 does not include 8, so I couldn't start at 7.5. I had to start at 8.5, and more than obviously means I'm getting bigger. When you have a less than or greater than or equal to, it's going to appear like things aren't matching up, but they are if you subtracted the 5/10 and you're going in the right direction. At most 8, well, at most 8 means 1, 2, 3, 4, 5, 6, 7, and 8 are good. 9, 10, and 11. At most 8 includes 8 and everything that's smaller than 8. You don't want 9 or 10. You want at most 8. So this translates to X less than or equal to. All right. So X less than or equal to includes 8. So I got to start here at 8.5, excuse me, and go to my left. If I started at 7.5, I would not include 8. X is fewer than 8. Well, what numbers are fewer than 8? 7 and 6 and so forth. Fewer than 8 does not include 8. So I couldn't start here at 8.5 and go to my left because I would go right over the 8. I'm starting at 7.5. To me, the easiest ones are the ones that go exactly, you know, X is equal, X is exactly 8. And then what you're doing is you're shading in from 7.5 to 8.5. These are the ones that are kind of no-brainers, the ones that are exactly. All right, so let me go through some of these here. I try to give you one of each with each example. A greater than, or equal to, a less than, and a less than or equal to. He says the probability of successes P is equal to 0.85. Find the probability that the number of successes R is greater than 280. Greater than 280. Well, greater than 280 translates to X is greater than 280, not equal to, greater than. What I've done here, he tells me, I'm going to actually do this one all out, even with a calculator. If P is equal to 0.85, if I can, my mouse wants to cooperate. If P is equal to 0.85, then it makes sense that Q is 1 minus that of 0.15. All right. And this is the way we're going to enter into the calculator to find the standard deviation. It's the square root of n, which in this case, n is 300. He didn't tell me here it was, but this, I should have had n is 300. That doesn't say, oh, here it is right here. There's 300, okay. N is 300, P is equal to 0.85, and then Q would be equal to 0.15. Here's where I actually figured out mu on my own. I wouldn't have to. I would have just told my calculator, hey, mu is n times P. Here I actually did it all out. And the reason I did that, I wanted to put the mean here. When you're doing these problems, you don't have to put the mean here, which is the highest point. Fact of the matter is, I want the area that's greater than 280. So greater means I'm getting bigger. Greater than 280. I'm going to my right. Now, greater than 280 does not include 280. To be bigger than 280 means you don't include 280. So I know I'm going to my right, but if I started here at 279.5, I'd go right over 280. I don't want to do that. I want to start at 280.5 and go to my right. Very important. 280 was the target point. Notice I didn't put 280 on my horizontal line. I just put it here. All right, and where you put it on the bell curve doesn't make a bit of difference. All right, I put the 280 here. I made sure I didn't put it down this horizontal line. And the first thing I did was to subtract 5/10 from 280 and then add 5/10. 280 plays no part in the problem. I know I'm getting larger, so I know I'm going to my right. Greater than 280 does not include 280, so I couldn't start here and go to my right. I had to start at 280.5 and go to my right. All right, and that's the area that I'm looking for. So 280.5 is my low value, my lower bound, and then I'm going all the way to I can't go any further. E99 is my upper. Now in the calculator, if I wanted the entire area that's shaded, my lower bound is 280.5. My upper bound is E99. Here, I didn't have to figure this out on my own. Just tell the calculator, hey, my mean is in the n value, 300, times the p value, n times p. There it is, n and p, n and p. Now, here again on the standard deviation, you're going to find the square root key. It's the square root of n, which is 300, times p times q. The calculator can handle all this. Matter of fact, it has it real well. Now, this is a weird one. He gives me an answer here of 1.870 e to the minus 5. What does e to the minus 5 would mean to take this decimal point and move it 5 places to the left. If I took this and moved it 5 places to the left, I'd have 4 zeros in front of the 1. So that's the whole thing done out. The next 4, I don't do all of this, but I will catch up to it towards the end. All right, what are we looking for here? Find a probability of at least 2 tickets this year. At least 2 means 2 or more. It's P is, as a inequality, it's P is find a probability that X is greater than or equal to 2. At least 2 includes 2. It'd be 2, 3, 4, 5, 6, and so forth. This is just to remind you on your calculator, if we had to figure out the whole problem, figure out the probability, I'd be entering this in my calculator. I'm not going to do that here. All right, so first thing I did was, here's my target value 2, but notice I didn't put it down in the horizontal line. I just use it as a reference point. I subtract 5/10 and I add 5/10 of 2. greater than or equal to includes 2. Well, I know I'm getting larger, but I don't want to start at 2.5 and go to my right because I would not include 2. I've got to start at 1.5 and go to my right. All right, I need to include 2. Now you're saying to yourself, well, 1.5 is not greater than or equal. That's because of continuity correction. Trust me, it is correct. Don't second guess yourself. Once you've subtracted 5/10 and added 5/10, you know you're getting larger, greater than, right? At least 2 means 2 or more. You're getting larger. The question is, do you start at 2.5 and go to your right, or 1.5 and go to your right? Since greater than or equal to 2 includes 2, you got to start to the left of 2 and go to your right. There's my lower bound and there's my upper bound. Find a probability of fewer than 5 passages. Well, fewer than 5 translates to the inequality x is less than 5. All right, so once again, this is just to remind you what's happening with your calculator. We're not doing it here. I'm just doing the left and right. So there's my 5. All right, subtracted 5/10. I added 5/10. Now less than means I'm getting small. I'm going to my left. Question is, a value is less than 5. Does that include 5? No, if you're less than 5, you're not including 5. All right, you're less than 5. So I'm not going to my left. If I started at 5.5 and went to my left, I go right over the 5. Well, no, I want values that are less than 5. So I'm going to start at 4.5 and go to my left. I don't want to include 5. My lower bound is negative E99 and my upper bound is 4.5. You would know what N is, you would know what P is, and then you could, if you knew P, you could obviously find Q, but it just takes some time. 6 takes the longest time. No more than 15, which means that 15 is good, but 16 is not. 10 is good, 9 is good, 8 is good. Anything lower than 15 is good. 15 is good. You don't want anything more than 15. That translates to x is less than or equal to 15. So I'm going to my left. Do I want to start at 14.5? No, I want to start at 15.5 because I want to include 15. X is less than or equal to 15, which means I include 15. If I start here, go to my left, I don't go over this. So I'm starting at 15.5 and going to my left. There's your lower bound and there's your upper bound. And this, the N and the P would be given to you. You can calculate the Q. The easiest ones are the ones that are exactly. Find a probability of exactly 24 felony indictments, heaven forbid. All right, there's my 24, subtracted 5/10, added 5/10, and everything in the middle. These are the easiest ones. It's kind of a no-brainers. There's your lower bound, and there's your upper bound. You're in business. All right, so what I've done here is these are a couple of problems from the actual assignment. N is 18, your p-value is 0.30. Find a probability of exactly 6. So those are the easy ones, between 5.5 and 6.5. Once again, I'll say this. If you're using a whole number like 6 for your lower or your upper, you're doing it wrong. There are no whole numbers. Your lower and upper D are going to be something that ends in 0.5 or negative or positive infinity. There are no whole numbers. There's my lower, there's my upper. My mean is N times P. I tell you what N is, I tell you what P is. Bingo. Standard deviation is the square root of N, 18 times P. Well, you know, if P is 0.30 or simply 0.3, then I know that Q is 1 minus that 0.7. So you're gonna be thinking a little bit. He tells me what Q is. I'm sorry, he tells me what P is, but you got to figure out what Q is on your own. How hard is it to take 1 and subtract 0.30 or subtract 0.3, 0.30, 0.3 are one and the same. And this answer has a lot of discrepancy, but there's only one answer that starts out with 0.19. If I'm not mistaken, and I get to be sure of this, when you do these, pretty much they'll be spot on. You won't find anything that's this far off. All right, but in this case here, there's only one answer that started out with 0.19. Fewer than 8. All right, so there's my 8, there's 7.5, there's 8.5. Fewer means I'm going to my left, but fewer than 8 does not include 8. So I'm going to start at 7.5 and go to my left. I'm not going to start at 8.5 because I go right over the 8. Don't want that. There's my lower bound, negative E99. There's my upper bound, 7.5. Mu is n times p. I tell you what n is. I tell you what p is. Sigma is the square root of n times p times q. Well, if p is 0.60, 1 minus 0.60, my q value is 0.40. And here's one that was just off by 2/10,000s, pretty darn close. Let's see, product manufacturing in batches of 120. There's my n value. The overall defect rate is 0.05. Here's your p value. Find a probability contains more than 6. Well, that translates to x bigger than 6. All right, more than 6 does not include 6. First of all, more than means I know I'm going to my right. Things are getting larger. I'm going to my right. Here's my 5/5. Here's my 6/5. Notice 6 didn't play anything in it. 6 was just a place for me to get started here, an access point or a relative point. All right, 5/5 and 6/5. Well, more than 6, x greater than 6 does not include 6. So I couldn't very well start at 5/5 and go to my right because I go right over the 6. I'm starting at 6/5. That's my low bound. E99 is my upper, n times p. Square root of n times p times q. Well, p is 0.05. Please don't use 5 for p. 5% is 0.05. Probabilities aren't bigger than 1. They're between 0 and 1. Don't make that careless error. In fact, I don't know what I think the calculator would actually give you some kind of error message if you put in 5 for p. 5% translates to 0.05. If p is 0.05, then q is 1 minus 0.05 or 0.95. So it's the square root of n times p times q. And this guy here was fairly close. All right, 0.41. There was only one answer that started out with 0.41. And once again, I'll say this won't be an issue because I'm thinking pretty much everything that I've given you on the exam is spot on. And if it's off, it'll be really close. There'll be nothing else even around it. 2% of the hair dryers produced in a certain plant are defective. Estimate the probability that 10,000 randomly selected hair dryers, at least 219 defective. At least 219 is x is greater than or equal to 219. Greater than, we're getting larger, all right? At least means we're getting larger, 219, 220, 221, and so forth. At least 219 includes 219. So I'm going to start at 218.5 and go to my right. If I started at 219.5, I would not include 219, which I need to do. There's my lower, 218.5, going all the way out to infinity. There's my n value times my p value of 0.022%, right here, 2%. And then sigma would be we can't see it because the calculator just gives me X amount of space. It's the square root of n, which was 10,000 times p, which is 0.02 times q. Well, if p is 0.02, then q is 1 minus that 0.98. Doesn't tell you that. I mean, if you were, well, I wouldn't even think you could put in 1 minus 0.02 here, but how hard is it to take 1 on a piece of scrap paper and figure out 1 minus 0.02 is 0.98? It is what it is. It's the most challenging one. It's the most challenging section. Find a probability that in 200 tosses of a fair die, we will obtain at most 30. At most 30 includes 30. Doesn't include 31 or 32, but it includes 30, 29, 28. We're getting lower. We're going to the left. At least 30 includes 30. So I'm going to start at 30.5 and go to my left. Everything here is good. Anything bigger than that is no good. So there's my lower, negative E99. There's my upper. Now, here's one where in every other problem, I've told you what P is. He doesn't tell you, but he tells you it's a fair die. Well, the probability of rolling a 5 is favorable over total. Well, how many sides to a die are there? 6 sides. On those, out of those 6 sides, how many of those sides are labeled the number 5? Only 1. There's only 1 5 on the die. Probability of a success is 1 chance in 6. We know this. We've done all kinds of problems dealing with rolling of the die. So it comes time to do the standard deviation. It's n 200 times p, which is 1/6. Well, if p is 1/6, then q is 1 minus 1/6. How many sides of the die aren't the number 5? Well, there are 5 of them: the 1, the 2, the 3, the 4, and the 6. 1, 6 plus 5, 6, you know, is going to equal 1. So if you know what P is, you know what Q is. It's rolling of a die. We've done a lot of these problems. All right. And the only one I didn't do is 1 in the middle, which is easy enough because it's subtract 5/10, add 5/10, and add everything. That's, I mean, shading everything in the middle. Those are the easiest of all of them. So give me a second. That's, you know, 6, 6 is all that and then some. It's, yeah, it's challenging. It's challenging. But I'm sure you guys can handle it because I'm still recording, which is good. And I want to go to 7-1. All right. Here's the gist of what's happening in chapter 7. What we want to be able to do is to estimate mu. We want to be able to estimate the mean of the average. Maybe we're concerned with the average age of everybody in the state of Massachusetts, or maybe everybody in the town of Brockton, or the average height of every student that goes to Massasoit, or maybe the average age of all the incoming freshmen. All right. So we haven't got time to go and survey everybody that goes to incoming freshmen. So what we do is we take a sample. Now 7-1 tells me, yeah, we're going to estimate the mean of the population. And suspiciously, we know the standard deviation of the population. You kind of scratch your head because standard deviation means how far the value is away from the mean. But yet we supposedly don't know the mean, but we know the standard deviation. All right, so in the real world, this is really iffy. This is the way the chapter of the textbook is set up. All right, section 7-1. You'll know you're in 7-1 because you just came out of 6-6. And you're also in problems dealing with 7-1, sigma will be given to you. There'll be they'll say sigma equals something. Oh, I'm in 7-1. I got to estimate the mean. All right. So we're going to have the mean of a sample. All right. We're also going to know the standard deviation of the population, which is iffy. And what he says here is that the mean of the sample is a good point estimate. And what they're saying is, let's say I'm in class with 25 people and I take the average of everybody in class and I say, maybe that's pretty close to the average age of everyone that goes to Massasoit. I'm using the sample as a point estimate for the mean of a larger population. Now, of course, if I had a big class, let's say I did a lot of classes, my point estimate, the mean of the sample would be maybe really close to the population sample, but won't be exact. All right, so we're going to use the sample mean as what's called a point estimate. And what we're going to do is come up with what's called a confidence interval. Because of time constraints, because of time and money constraints, difficulty in finding population members and so forth, we usually don't have access to all the measures of an entire population. Instead, we rely on information from a sample. This is how things are done. When pollsters go out and find information, they don't survey everybody in the country. They use the sample. In this section, we develop techniques for estimating the population mean mu by using sample data. We assume we somehow know sigma, which is nonsense. All right, this won't happen in the real world, but this is how he starts it out. An estimate of the population parameter given by a single number is called a point estimate. We're going to use X bar, the mean of the sample. He says, even with a large random sample, the value of X bar, the sample, is usually not exactly equal to the population mean mu. There's what's called a margin of error. We're a little bit off. We're off on the low end and we're going to be off on the high end. All right. The margin of error of the sampling describes how close we can reasonably expect a survey result to fall relative to the true population. For instance, a margin of error of plus or minus 3 points at the 95% confidence level means if we fielded the same survey 100 times, we would expect the result to be within 3 percentage points of the true population 95 out of those 100 times. And you see that a lot with national surveys. They'll go, this is the percentage of people who have been vaccinated plus or minus 2 points. That's what's called the error. All right. And how 7-1 starts out, there's three things we're going to do in 7-1. One of them is simply to calculate the error. The second thing we're going to do is we're going to calculate the confidence interval. The calculator will do this. The third thing we're going to do is to calculate the sample size we need to know. There's no calculator function for that, but there's a formula. So the first thing we start out is, hey, just give me the error. All right. And this was these Z-scores come into effect. And I showed you that list of PowerPoints. I had critical scores for section 7.1. This is what I'm talking about, the Z-score. I could have brought you to a table. I could have brought you to a table and had you figure out the Z-scores. No, I flat out just give you the critical value. We're going to be working with what's called confidence intervals and confidence levels. Levels range from like 70% all the way down to 97%. So if I'm saying, hey, listen, I want you to work with a 85% confidence level, then you know your critical value, your Z-score is 1.44. I give you all of these. This slide you've got to have, because if you don't know these critical values. Because to figure out the error, you need that critical value. You'll be given what sigma is, because you know sigma. You'll be given what n is. You're just going to multiply by this times this divided by the square root of n. All right, so you've got to have this chart, because without it, you're lost. Julia enjoys jogging. She's been jogging over a period of several years. All right, so she's got a lot of times logged in. During this time, her physical conditions has remained constantly good. She jogs 2 miles per day. Standard deviation is 1.80. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 times. The mean of that sample is 15.60. All right. Let mu be the mean time of all of the times that Julia has gone jogging. He says, come up with a 95% confidence interval. We want to be 95% confident that the interval we come up with does contain the true mean of all the times over these years that Julia's been jogging. That's the idea. All right, so the first thing we want to do is calculate the error. Well, here's the formula for error. It's a Z-score times sigma divided by the square root of n. Well, I went to my chart in the previous slide, and for a 95% confidence level, the Z-score was 1.96. I'll show it to you again. There it is, where we already at 95% confidence. You see 1.96. All right, so there it is, 1.96. I tell you that sigma is 1.80 divided by the square of n. Well, Julia, sample contained 90 samples. That was my n. There was 90 of them. And all I'm doing is putting this into the calculator. There's my critical value, my Z-score. There's my sigma divided by the square root of n. And we come up with 0.37 to correct 2 places. All right, and this is just doing it pencil and paper. This is using the calculator. Why would I want to do pencil and paper if the calculator do the multiplication and division? Easy enough. You know, all you do is look up the critical value associated with 95% confidence interval level, 1.96. There it is. You're given this, you're given that. Put it into the calculator, no big deal. Now, if I was going all the way with this, what I would do is take the mean, which was given to me as this, I would subtract the error on the low end, and I would take that X bar and I would add the error on the high end if I was doing it pencil and paper. But we're not going to bother doing that. All right, let our calculator do it. Now, to let the calculator do it, we're going to a different menu. We're just hitting the stat button, not second function, just hitting the stat button. We're arrowing over to test, and I'm coming down to Z interval. All right, there's two things. He's asking me, do I have raw data or do I have statistics? I've got statistics here. All right, What's sigma? It's 1.80. What's my X bar? It's 15.6. What's my end value? My end value is 90. What's my confidence interval? My confidence level? It's 95%. Here again, I could use 0.95 or I just use 95. The calculator for some reason doesn't mind if I just use the whole number. But here's the key thing. Look at this here. Look at this interval between 15.23. See it, pencil and paper? And on the high end, 15.97. Spot on. Chapter 7 is great because all the answers are spot on to what you're going to see on the exam. And pretty much all of them are, but 7's always been this way. Pretty nice. What are we looking for here? I'm just looking for the error. All right, so we're looking for a 99% confidence level and it's 76 X bar. Well, in finding the error, I don't even need X bar, but I do need sigma. All right, there's a little formula. It's a Z-score. The Z-score that's associated with a confidence level of 99%, according to that chart, is 2.575. My sigma value is 872 divided by the square root of n. I put this in parentheses. You didn't have to. If I didn't want to use parentheses, all I would have to do is put a time sign here. And I wouldn't need a closing parenthesis. I just did this for emphasis sake. All right, and round it to the nearest whole number because all of these were round to the nearest whole number. 257.7 was 258. And there it is, 99% confidence. My Z-score, or Z sub C, he calls it. All right, Z sub C calls it. It's 2.575. All right, so that's finding error. Now we move on to finding the whole confidence interval. And I've just highlighted the important information. There's my sigma. There's my n size. My n is 16. My mean is 50. I'm looking for a 90% confidence interval. I'm still working with stats. Stats means he's giving me sigma. He's giving me the mean. He's giving me the n. That's stats. Sigma is 6. There's my X bar 50. There's my n value 16. There's my, I just use 0.9. 90% could be 90. Could be 0.90, could just be 0.9, all kind of ways of entering it in. All right. Normally, I just would have put 90. For some reason, I put in 0.9, which is the same thing as point. The calculator doesn't seem to mind. All right, 0.9, 0.90, or just plain the whole number 90. Key thing is there's my interval, there's my low end, and there's my high end. This will match up perfectly with the answers on the answer sheet. All right, so 3 things here. First of all, we started out with finding the error. All right, your Z-score times sigma divided by the square root of n. To find the entire confidence interval, I hit stat, arrow over the test, came down to Z interval, put in my information, and the calculator did a wonderful job. Flip the script. Now he wants to know the sample size. In the design stages of any statistical research, it's a good idea to decide in advance on the confidence level you wish to use, select the margin of error you want, and after you make those choices, right, you need to know how big of a sample, all right, how big of a sample size should I be taking? Should I be sampling 100 people or 500 people if I want to be 95% confident? You gotta have an idea of how many people you're going to be working with, all right? So this section, this last part of 7.1 asks you for, hey, how big of a sample do I need? Translated means you need to find the end value. Well, if I take this little error formula, and I do a little bit of algebra and I solve algebraically for n, I come up with a little formula here, right? Taking this formula and modifying it, I have n equal my Z-score times sigma divided by the error, and all of this quotient squared. So when you're doing these on your calculator, you got to start out with an open parenthesis, put in the Z value, put in the sigma, divided by, put in the error, close your parenthesis up, and then you need to square using the square key. Now, let's say, for instance, you're doing it and, oh, I didn't square it. All right, then don't bother, take the Z-score times sigma divided by E, get an answer, and then square the answer at the end. I'd rather do it all in one step by enclosing the formula in parentheses. All right, open parenthesis, put these 3 numbers divided by, well, put the 3 numbers in, square, close up the parenthesis and hit the square key. A wildlife study is designed to find the mean weight of a salmon caught by the Alaska Fishing Company. Primary study of random sample of 50 salmon is my end value. Showed that sigma was 2.15. Says, how large of a sample should I take if I want to be 99% confident that the sample mean is within 0.20 pounds? Well, there's my error. Within 2.20 pounds, there's my error. All right. So a lot of times in these problems, he says, oh, by the way, there's your error. He tells you it, but you gotta, you gotta kind of like figure out that, oh, he's telling me the error here. Sample mean is within 0.20. That's the error we're looking for. All right, so we know that the Z-score associated with a 99% confidence interval according to the chart is 2.575. The error is 0.20. Well, there's my little formula here. All right, it's the Z-score, which I knew was that according to the chart. I was given what sigma was. I know what the error was, so I'm putting it all in parentheses and I'm squaring it. What I did here is I put these two values in parentheses by themselves. I wouldn't have to. Don't need them. All I need to do is put that number in times the sigma 2.5 divided by 0.2 or 0.20, close parentheses up and square it. The deal is here, you always round up to the next highest number, no matter what the decimal is. 769 rounded up. The next whole number is 770. So I would need a sample size of 770 to be 90, what was it? I wanted to be 99% confident that my values were within 0.20 pounds. Here again, find the sample size. Well, there's a formula right there, all right? And it's my Z-score, the Z-score that's associated with 95%. There it is, 1.96 times sigma. He gives me sigma, 593. Got it. Divided by my error. He tells me, I mean, this formula calls for three numbers and they give you the three numbers. Pardon me if I giggle, I laugh here. All right, so all you're doing is, you're putting in your Z-score times your sigma divided by the error, and you're squaring the whole quotient here. All right, 93.8 rounds up to 94. No big deal. If you think about what you had to do in section 6.6, 7.1 is a breeze because everything is given to you. Big deal. You got to go to a chart. But that's the hardest thing I got to do is go to a chart to find out a critical value associated with a given confidence level. I'm looking pretty good here. All right, that's all there is in 7.1. Three things. Find the error. I'll give you the formula. Find the whole confidence interval. You hit stat, you arrow over the test, come down to Z interval, all the numbers that it wants, because it's all stats. Notice in 7.1, we just use stats. We never had to use data. Not going to be the case in this very last section. Stats was all we had. I gave you sigma. I gave you the error. I gave you what the mean was. I didn't give you what the mean was. I gave you what standard deviation was. All right, so let me close this up. I stop sharing that. And I want to go to 7.2. You should all be seeing my 7.2. Hello?
Yes.
Fantastic.
Yes.
Thank you. Thank you. Slideshow and starting from current slide. All right, this is more in tune with reality. We still want to estimate the mean of the entire population. But now we don't know what sigma is, which is, you wouldn't know. If you don't know the mean, you're not going to know the standard deviation. So that was kind of nonsense. All right, that was nonsense. Here's the main difference. Back in 7.1, all right, we knew what sigma was. Sigma was the standard deviation of the population. In 7.2, we're going to be given the standard deviation of the sample, which makes a lot more sense. All right. We're not going to be given sigma, we're going to be given S. Instead of using this Z-score from that chart, we're going to use what's called a student distribution. We're going to be using T-scores. This is the major difference. We don't know this, but we're given S. We went to a table, we found the Z-score. Well, we're going to go to a different table and find a T-score. This is 7.1, this is 7.2. That's the distinction. All right. these values change, and then you don't know this, but you do know that the square root of n doesn't change at all. That's the whole key to this. In order to use a normal distribution to find a confidence interval, mean mu, we need to know the value of sigma of the population standard deviation. However, much of the time, when you don't know the standard deviation, we don't know the mean, the population mean, you don't know sigma as well. He says, hey, if we don't know sigma, we're going to approximate it by using the standard deviation of the sample. That's called S. When we use S to approximate sigma, the sample distribution follows a new distribution. It's called a student distribution. And this doesn't mean a hell of a lot, but it's this guy named Gossett came up with this, and he worked for this company, a brewing company, and he was trying to hide the fact that he was not doing his work. He was working on statistics. So he published it under a pseudonym student. He doesn't know his last name was Gossett. Little trivia there. It's called a student distribution. Okay, started back. This guy was doing this back in 1908. All right. The student distribution makes use of something called degrees of freedom, DF. And simply stated, degrees of freedom is the n value subtract 1. All right. The T distribution, the student distribution, uses something called degrees of freedom on the chart. DF, degrees of freedom. So what does it really mean? What does this degrees of freedom mean? All right. Here's an example. Let's assume Brenda's final average in stats is 85 after 4 exams. All right. If we take 85, multiply it by 4, we know that Brenda scored 340 points. 85 times 4 is 340, or 340 divided by 4 gives her her average of 85. Got it. Using degrees of freedom, we could assign Brenda any score we want for the first 3 exams. For instance, let's say we guessed that she had a 73 on the first exam, a 95 on the second, and 81 on the third. If I total those points up, I come up with 249. Now I know her average is 85, so she has to get a total of 340. So if I take 340, subtract what I assume maybe she got on the first 3 tests, that gives me 91. She has to get a 91 on her last exam. Stated simply, with 4 exams, the first 3 could have any score, but the last score had to be a fixed score. In this case, it had to be a 91 to get her up to 340 points. Stated another way, we have 3 degrees of freedom. Her first 3 tests, we were free to pick any value we want. So that's this idea that you're going to see in this chart. I thought I'd take the time to explain what degrees of freedom mean. Degrees of freedom is your n value subtract 1. In this case here, we had 4 tests, subtract 1, which means these 3 exams could be anything we wanted them to be. And that last exam had to be exactly, in this case, 91. So here's the chart, okay? Now, these are all your degrees of freedom. These are not your n values. These are n values subtract 1. And the only thing you're going to be using across the top here is this very last row. There's a confidence level of 50, there's 75, there's 80, there's 85, there's 90, there's 95, there's 98, there's 99, and there's 99.9. You'll never use this one. In most cases, it's either going to be 90, 95, sometimes it'll be 99. Very rarely do we use these numbers here. When working in section 7.2, usually your confidence level is 90%. Could be 95, maybe 98. A lot of times it's 99. We never use 99.9. So these 3 are the major ones. Actually, these 4 right here are the ones we use. But remember, this column here, as we match these things up, degrees of freedom with the confidence level. All right, these are not n values. These are n-1s, degrees of freedom. And once again, we start out the same way we started out in 7.1. Let's just calculate the error. The error is the t-score times s divided by the square root of 1. So in this first problem, I tell you that n is 21. I tell you what x bar is. Well, x bar plays no part in finding the error, okay? But I do give you what s is. Well, if n is 21, then degrees of freedom is 21. Take away 1, subtract 1 is 20. So on the left-hand edge, I find degrees of freedom 20. Now I'm looking for a 95% confidence level. Well, there's 95% there, 0.95. Where this column and this row meet, there is my T-score. I'm not using Z-scores, I'm using T-scores. It was easy enough to find. All I do is to take 1, subtract it from 21, find degrees of freedom 20. There it is. And then match it up with 95%. And where these two guys intersect, 2.0, 2.086. I tell you what S is. Up at the top, I tell you that the standard deviation of the sample is 0.16. There it is. Divided by the square root of n. Now, n was given to you as 21. The only difference is that you had to find this T-score, and you needed to take 1 from n and match it up with the confidence level, in this case 95%. And there it is. The answer is points. The calculator gives you 0.073, spot on to what's given here. Second one here is n is 51, which means my degrees of freedom are 50. I'm looking for a 95% confidence level. Well, 50 and 95 intersect at 2.009. So there's my T-score. S is given to me up here as 202. I got it, divided by the square root of n. N is given to you as 51. 56.8, spot on to what you see here for the answer. All right, just finding the error. Same thing you did in 7.1. All right, so I give you some information here. Suppose X is a mound shaped distribution. Sample size n is 16. Sample mean is 10. Standard deviation is 2. Now, he says standard deviation. He's talking about, no, he says sample mean. We know that's S. Standard deviation is 2. Well, degrees of freedom is n minus 1 is 15. Looking for a 90% confidence interval. All right, so there's my 90%, there's my 15, and they intersect at 1.753. There's my T-score. Now, look what would have to happen if I was doing this pencil and paper. All right, you know, my mean falls between my low value and my high value. What's my low value? It's my X bar minus the error and X bar plus the error. You know, look at all the mathematics you would have to do here to get the confidence interval, but you don't have to do that because your calculator is going to do it for you. All right. How does my calculator do it for me? Well, the same thing we did back in section 7.1. I hit stat, I arrow over the test, but now rather than coming down to 7, which I did in section 7.1, I'm coming down to number 8, which is T interval. I use Z interval for 7.1. I use T interval for 7.2. All right. And once again, I have stats. Stats means I know what n is, I know what the mean is, and so forth. I have stats. X bar is 10. The mean is 10. It tells me it. My standard deviation is 2. I tell you what standard deviation 2. My n value is 16. You're given to you. You need a 90% confidence interval. Well, there it is, 90. I mean, it requires you to put in 4 numbers, but the 4 numbers are given to you. You hit enter. And it comes out to be, this is the answer we got when we did all this mathematics here. Let's see if I can find it, if I can go back up. Previous slide. No, I don't want to do that. Yeah, here it is right here. Well, trying to be cute here and I can't be. Bottom line is your calculator gives you the answer. This is the answer we got when we did all that mathematics. So we didn't do it, but the slide did it. Spot on. Your calculator does it. Once again, stat, arrow over the test, come down to number 8, T interval. Here I give you all the information. I give you N, I give you X bar, I give you S, I give you the confidence level. All right, so it's still stats, X bar 83.1, S of X, there it is, your S value. The samples mean 6.4. You're given N is 30. I'm using 90. I could have used 0.9 or 0.90. Didn't make a difference. But the key thing is look at how your calculator gives you and look at the answer right on the money. There's no discrepancies whatsoever, which is kind of neat. All right, now how do things change? Here, I give you a bunch of raw data. The slide here went and took this raw data, found the mean, found the standard deviation. No, I don't need to do this. If I'm given raw data, how I accomplish to find the answer is fairly straightforward. If I'm given raw data, I don't want to do all of this mathematics. Trust me, you're not going to have to do all that. He's calculating the mean, he's calculating the standard deviation. No, we don't need to do all that. If I'm given raw data, once again, I go to stat, arrow over to test, come down to number 8. Usually, if you just finish the problems, this is being highlighted. So the minute you see raw data, you have got to arrow over to the left, data, press enter. All right. Now, where is my data? Well, here again, I always like to put things in list 1. I put all these numbers, 2, 4, 6, 8, 9 numbers. You don't see them all because calculator just shows you X amount of space here. I put those 9 numbers in list 1. Make sure data is selected. Where are my values? They're in list 1. The frequency will always be 1. All right, it's not a frequency distribution. Frequency will always be 1. What's my confidence interval? 90%. And that's all you need to do. And it gives you your confidence interval between 1249 and 1295. All right, just add 9 numbers. I think on the test, I know you have one like this, maybe 8 numbers. No big deal. Put them into the list. If you're not using list 1, please remember where the heck you put them. I think list 1 would be the place to put it. This is data. You're not using stats, you're using data. All right, same thing here. You're given raw data. All right, so you go to stat, arrow over to test, come down to number 8. Make sure that data is highlighted. I got my numbers in list 1. All right, there it is. Frequency will always be 1. My confidence interval is 90%. There it is, 90. Hit calculate, and knows the answer. So basically, it just requires 2 inputs. Well, it took maybe a minute or 2 to put these 6 numbers into a list. Maybe a minute. All right, but that's what you have to do when you're given raw data. And definitely, you will see one on the exam. And that's it. There's nothing to do with sample size. All right, it's either find the error or it's give me the confidence interval. Sometimes you're given all the information, you're given stats, and sometimes you got to put the numbers into a list and choose data. So I'll stop the share there. Let's just close these guys down and close this. All right. So that took me about an hour and 10 minutes. Now, as I shot you an email, I think it was Sunday night, I kind of told you, I told you what I was going to do. And then I said, have any questions ready for me so we're not wasting your time and for me, more importantly, wasting my time. But I don't want to cut it short. If you have any questions, I want to take the time to answer them because tomorrow is a make or break day. Traditionally, I don't know. Let me just say this. Looking at the stats, when I look at Canvas, I got some people that put in 50 hours. It gives me the cumulative time. I see people that have been online 50 hours, looked at, hundreds of pages. And then I find people who spent maybe 2 hours. But then again, it doesn't equate to grades. Some of the people who spent the least amount of time did the best on the first test. So you like to make a correspondence with time, but truth be known, time in is going to equate to knowing something in most cases, but it is what it is. It's a free country. The stuff has been there. Some of you put the time in, some of you maybe not, but put it this way, it'll all come out in the wash tomorrow. That's for sure. That's for sure. So does anybody have anything that they want me to clear up, since it's the last time we'll be quote unquote looking at each other? You'll be hearing my voice.
Do you think you'll add like questions from the previous exam?
4-3, once again, I'll say this again, 4-3, 5-2, 6-2, 6-3, 6-5, 6-6, 7-1, 7-2. Ms. Fernandez, we got enough stuff to do. I'm not going back to no, it's not cumulative. I'm not going back to chapter 1 or chapter 2. It's just where we started off with 4-3 at the end of chapter. The end of the first exam stopped at 4-2, so I'm picking it up at 4-3.
Okay, sounds great.
Unless you want me to go back just for you, go back to
No, thank
section
you.
3.
Yeah, I like it better starting at 4.3.
Yeah, I would like it too. Trust me, we got enough to do. You know, statistics is strange in that for every other course I've ever done at Massasoit, and I go back to doing courses years ago, like fundamentals, shoot me now, please. All the way up, I've done pre-cal and whatever. Stats is one of the ones where there are several books being used by different professors. So the math department has never come up with a standardized departmental final. They pretty much give the professors freedom. And my way of doing it is just to have 2 exams and make the last exam, the so-called final, not cumulative. You got enough to memorize for tomorrow, then going back to 3-2 and whatever. Make sense?
Yes.
Okay. Good question. Portuguese, Miss Fernandez, or Cape Verdean?
I am Cape Verdean.
What island?
Fogo.
Too bad if you said Bravo, you would have gotten 10 points. Want to ask you again, Miss
My
Fernandez.
grandmother was born.
Did I- Huh?
My grandmother was born in Brava, but she moved to Fogo.
Oh, she married somebody in Folk?
Yeah, my grandfather.
Why did all the men go to Brava for the women? Why is that?
I guess they were cuter there.
Oh, yeah. You know it. My grandpa did the same thing with my grandmother. He was from Fogo, my grandmother's from Brava. Yeah, they found a way to find the cute girls.
True.
True. You ever been there?
No, I've only been to Fogo, but I do
Oh, you've
plan on
been to
going
Cape
next year.
Verde. Good, lucky you. I've never been.
Really? You should go. It's a beautiful island.
Got any money for me? You gonna buy me a ticket?
Yeah, that's a little.
Yeah, about 1,800 bucks, I heard. It's on my bucket list.
You should go. Do you speak Cape Verdean Creole at least?
Papi Creole, a little bit. Yeah, you know, it's funny because my mother and father never spoke it at home, and I knew whatever Creole I knew was I used to board with a woman named what was her name? Hi, Patience. Can't even think of it right now. And she only spoke Creole to me. So whatever words I did know, I learned from her. But it's so nice to speak your native language. Do you speak fluently?
Yes.
Oh, yeah, you know, and it's funny because different islands, different dialects. You know, it's like with
True, like
Spanish.
different
Spanish
accents.
in
Just like
Spain is different from the Spanish in Puerto Rico, different from the Spanish in Mexico. As you well know, the different islands have a little bit different dialect.
I feel like San Vicente is the more outstanding one.
Yeah, San Vicente's a nice island. It's the classical island. My wife's people are
Really?
from San Vicente. And actually, yeah. And my folks are all from Jabra. You know what's
At least-
weird? Talk about being not. Here we
At
are,
least-
9 different islands, and
Yeah,
we're prejudiced amongst ourselves. Isn't that sad?
it is.
You know, when I was getting married, I was supposed to marry somebody from Brava. I mean, how dumb is that? And then you find Cape Verdeans who are very light skinned. My mother was as light as can be, and my dad was darker, you know, and then it's weird how we can be 9 stupid islands and be prejudiced amongst ourselves. You know, the color of your skin, the quality, the straightness of your hair. It's sad. We're all from the same place, you know, it's wacky.
But it's
Pretty
probably
old.
because like there's like certain islands that have more of like Praia has more of like badius and stuff. So
Yeah, yeah. And of course, if you go to school in Cape Verde, you speak Portuguese, Portuguese from
Yeah.
Portugal.
and
But
they learn cursive still. They enforce cursive onto students,
do
which
they?
is in my
Well,
opinion.
no one else wants to talk to me, so me and Miss Fernandez are having a conversation here. If you have no questions, I've had a long day. I'm sure you've had a long day. You've got a lot. You got 3 hours. Don't rush through this. You got 3 hours to do this. But once again, word to the wise, have those sheets by your side. and have maybe how you get to the correct menu item, just a little note. Hey, I need to go to stat and come down, go over the test. Or I need to go to second function vars, normal cumulative. Or back in, doing permutations and combinations, I need to hit the math key. Arrow over to PRB, probability. I'll see the exclamation point for factorial, and I'll see NPR, and I'll see NCR for combinations. So make sure you have everything before you start the exam. Get prepared, have everything. If you're doing it at a desk or a kitchen table, have everything there. You guys know how it was. You saw the first test, and if you looked at the practice examples, they were very similar. There were different numbers, but the exact same problems. And then to top it off, I don't mix them up. I give you to them in order: 4-3, followed by 5-2, and I label them: 6-2, standard normal; 6-3, non-standard normal; 6-5, central limit theorem; 6-6, continuity correction, subtract 5/10, add 5/10; 7-1, sigma will be given to you. All right, you're hitting stat, you're going over the test, you're coming down to Z interval, number 7. For 7-2, you're in 7-2 because sigma will not be given to you, S will be given to you. But make sure you get that T distribution, because to find the correct T value, you're going to subtract 1 from N, degrees of freedom, match it up with the confidence level, find that T score, S will be given to you, N will be given to you. And then, of course, you have the formulas to find sample size. Folks, I've given you all the material, everything you need to succeed. If you've been conscientious, you can't play catch up now. If you haven't put any time into this since the last test, it's going to be difficult for you. But if you've been conscientious and been logging in, and I see who's been logging in to a certain extent. If you've been conscientious, this is going to be a breeze for you. If you, for one reason or another, haven't done your due diligence prior to this, I wish you luck, but then again, you knew what you were getting into, because it's a 5-week course, and guess what? It's over as of tomorrow. You've completed something that normally takes 14 to 15 weeks. You've knocked it out in 5 weeks, but it's been a lot of work, and I wish you guys to get some great averages going, and hope you keep it up for tomorrow and things are good. The average that you see may not be the average that you end up with. I will not deduct points, but some people are going to get extra added points. And usually it's those people who I know have logged in every one of my meetings. All right. And I have attendance going back to the very first one. So if anything, your average will increase by 3, maybe 4 points. I won't subtract any points, but the people who, for one reason or another, haven't logged in every Tuesday or Wednesday, you're not getting the same points as someone who has logged it. That's just the way it is. Rewarding the people who've done what they were supposed to do. I mean, going way back to you signed up for this course, you knew that Wednesdays from 7 to 9, you had to be there. And I know life gets in the way. I mean, there's people who've come down sick, you've had family members, but I can't control that. I really can't. All right. If you had a viable excuse that I bought into, well, fine. I'm not going to penalize you if you had a valid excuse. Obviously, a child getting sick is a decent excuse. It's acceptable, but I'll figure that out. So all that being said, if you're debating, does anyone know how fast Massasoit posts the grades online? How soon after the course ends do you look and see your grades?
Well, I mean, typically, like when the exam uploads and it gives you Canvas shoots out your final grades. After that, that's pretty much your grades. So honestly, even if you don't check on Massasoit, Canvas pretty much shows you your.
Yeah, what I'm saying is though, your Canvas score may not be your actual score. If anything, it'll be higher. You follow what I'm saying? Because I always credit people a few extra points. You follow? And I do that because of the fact that doing a 5-week course and doing, what I'm doing, I'm taking into account we're still under this COVID thing. I was out today at different stores wearing a mask, so I give people a couple extra points. So if anything, the grade you see, it won't be any lower than that, but there's a good chance it may be higher. And in a lot of cases, I've been doing this for a lot of years. A lot of times I get people with 78, 79s. I get people with 88s, 89s. And if you've been due diligent and you've been logging in, your grades are 89 and you've been logging in, I'm going to give you the extra couple of points. You follow me? I'm going to help you out here. Make sense?
Yes.
And if you're from Cape Verde, raise your hand. How many people from Cape Verde here? Ms. Fernandez, the only one who's getting the points then. Selena, you from Cape Verde?
I mean, I was born here, but my family's from Cape Verde.
All right, it gives you half a point. You make Gufung?
I don't know about that one.
You don't know what
Wait,
Gufung
what
is?
did you say? It's to make
Ms.
what?
Fernandez, tell her what Gufung is.
Oh, it's a really, it's like it's like a hot dog, but it's not a hot dog.
No, it's shaped like a. Tell her go to Vincente's and buy some Gufung. You're familiar with the Vincente's?
Yeah.
Yeah, get some
I get
Gufung.
pastel and terasma for my dad.
Yeah. If there's no other questions, I'm gonna sign off. Good luck tomorrow. Bon chance, as we say. I'm hoping you guys all do well.
Thank you.
If you have a last minute question, shoot me an email. I should be around tomorrow morning. I should be, we'll see. But you got from 11 tomorrow to 11 Thursday, and I wish you well. It's
Thank
been a
you
pleasure
so
meeting you,
much.
and maybe we'll, anyone
Have
going
a
back
good
to camp?
night.
Anyone going to campus, going back to campus live next semester?
I am.
I am.
Thank you. Bonjour.
All right, I'll be on campus on Tuesday mornings. I'm doing, what am I doing? I'm doing college algebra.
Yes, me. I am.
College algebra? Okay. All right, guys.
Have
you
a good
later.
evening.
You as well. Say hi to Mom, Katrina.
I will. Thank
All right, see
you.
you later. Bye-bye.
Alrighty. Bye-bye.